In this course, we are going to build the blueprint for a door that interacts with a lock, key, and switch. To open the door, the player will need to pick up the key, then use it on the lock, and finally press the switch to open and close the unlocked door. Each of these objects will be a separate actor that can be placed in the world anywhere. They will communicate with each other through their blueprint event graphs. Let's get started by cloning the basic player controller project that was created in the first video of this series. This project is called GDF101. It'll be used as the starting point for many of the videos in this series. Now that we have a working copy of the player controller project, let's begin setting up the world by moving the player start object to a more useful location. Set it to 2200, 0, 400, and then set the Z value of the rotation to 180. Let's also rotate the directional light to make it easier to see all of the objects we're going to add to the scene. Set its rotation to 0, 220, and 15. We can now begin building the door blueprint. Create a new folder in the content drawer called Door. Let's also create a new folder called Interfaces. We will create all of the blueprint interfaces we will need for the entire project, so we don't have to come back here over and over as we progress. Create 4 interfaces. Name them BPI Pickup, BPI Switchable, BPI Unlockable, and BPI Usable. You could also duplicate your first interface and just rename it each time. The BPI prefix we're using simply stands for Blueprint Interface. Let's now define the functions for each of these interfaces. The usable interface needs one function called use. This function has no inputs or outputs. The pickup interface needs one function called pickup. It will have one output called outSuccess, which is a Boolean. This will tell the caller of the function whether the object was actually picked up successfully or not. The unlockable interface needs one function called unlock. It will have one input called inKeyActor, which is an actor object reference. This is the object the player is trying to use as a key to open the lock. It will also have one output called outSuccess. This will tell the caller whether the lock was opened successfully. Finally, the switchable interface needs one function called switch. This function also has no inputs or outputs. That's all of the interfaces we need for the entire project. We will now extend the main characters so that they are ready to pick up objects in the world. For right now, the only objects in the world will be keys, but we can later add new objects that can be picked up using the same interface. Open the main character blueprint. Begin by adding a camera component to the character. After we have the camera, we can add a scene component as a child to the camera. Call it hold point. A scene component represents a location in the world without any other functionality. This will be the place where the player holds any object they have picked up. We will position this component in front of the camera so that any object being held by the player can be seen by the camera. First, move the actual camera up to 50 on the Z-axis so that it's closer to where the player's eyes are located. Since the hold point is a child of the camera, it will also move up to the same location. But let's offset the hold point a little more so that it appears slightly off-center, as if it is being held in the player's right hand. When making small edits like this in the viewport, it can be convenient to slow down the camera speed. You can do this with the option at the top right of the viewport, but if you can't see this icon, you might need to expand the viewport until it shows up, because when the viewport is small, it is hidden. Let's define a variable that can store a reference to the actor the player is currently holding. Call this variable heldActor and set its type to an actor object reference. Define a second variable called useDistance and set its type to float. This will represent the distance at which the player can attempt to use any object in the world. The next thing we want to do is define a begin overlap event for the main character's capsule component. After clicking on the capsule component, you can automatically create the begin overlap event by selecting it from the list in the details window. You can also do this by right-clicking on the capsule component and selecting the event from the context menu. If done correctly, this should automatically jump your editor to the event graph showing the new begin overlap event. We now want to revisit the use action that we created in the first video. This action currently just prints a debug string so that we could see it was working, but now we want to introduce a real use feature. Begin by deleting the print string logic. We are going to use a ray trace to search for objects in the world that the player might be able to use. Add a line traced by channel node to the event graph. In order to define a line trace, we need to supply two vectors. One is where the line begins and the other is where it ends. To calculate these two vectors, we will use the position of the camera. Call getWorldLocation and getForwardVector on the player's camera component. The forward vector is a vector that points in the same direction the camera is facing, and it is automatically normalized so that its length is equal to 1. We can use the camera's world location directly as the start for our line trace. To get the end position, we need to add the camera's world location to its forward vector. This will give us a vector that points from the origin to the correct ending point along the direction the camera is facing. But we also need to multiply the forward vector by the use distance variable we defined earlier, so that the vector's length is equal to the use distance. Otherwise, the player would only be able to reach objects that were 1 centimeter in front of them because of the length of the normalized forward vector. Let's also set the draw debug type to for duration so that we can see the line trace while we're playing the game. This will help us catch any errors in our math. That's all we need to do to set up our line trace. It may be confusing why we need to add the forward vector to the world location to get the correct end vector, because you might picture the camera's forward vector as starting at the camera's position. This would make it seem like it already points to the correct end position. In this position, it looks like it already perfectly describes the exact line trace we want to perform. But the forward vector does not start at the camera. An important thing to remember with vectors is they always start at the origin. It is part of the definition of a vector. A vector begins at the origin and points to the position defined by its components. The components of a vector are defined in terms of their distance from the origin. They don't even make sense without reference to the origin. Many references will say that vectors can be placed at any point and they do not start anywhere, but in practice this isn't really true. First, recall that you can add any two vectors by drawing a parallelogram like this. You get a plus b by drawing a vector that starts at the origin and ends at the opposite corner. This is always how you add two vectors, and notice it is symmetric. A plus b is the same as b plus a. If we want to describe an arrow that starts from some other place than the origin, then we need to supply additional information about where that arrow starts and ends. It can't be expressed by a single vector. So the actual content of a vector is an arrow that must start at the origin. That's the only thing a vector can express by itself. If we want to describe something like arrow A that is similar to our line trace, we need to give two vectors. We will call them start and end. To find the end vector, we need to add the start vector to vector A. Notice every vector still starts at the origin in this picture. We can also see this by looking at vector subtraction. Recall that to subtract vectors A and B, you can add A to negative B, which is the vector that points in the opposite direction with the same length. After drawing negative B, we can use the same parallelogram rule for addition to find A minus B. In math class, they may have said that subtracting a vector A from a vector B gives a new vector that points from the tip of B to the tip of A. But you can see from this picture this isn't true. The new vector starts at the origin, like all vectors do, and points to a position that is not on A or B at all. What is true is that A minus B will point from B to A if you move it over until its starting point lines up with the ending of B. But to describe that movement requires a second vector, so we are no longer talking about a single vector. It's even worse because you can see from the picture that the end vector we would need is A minus B plus B, which is just A. So all we've done is once again describe the arrow from B to A by giving two vectors, which are the same two vectors we started with. So, do not think of the camera's forward vector as starting at the camera and pointing in the direction it is facing. Do not think about any vector as starting anywhere except the origin. This will help avoid a lot of confusion. The wrong example here shows what happens if we try to use the camera's location as our starting point and its forward vector as our ending point. This creates a line trace in red that doesn't even point in the same direction the camera is facing. The correct example shows how we can add the location and forward vector to find the end point for our line trace. This gives us a line trace that starts at the camera and points in the direction it is facing, and it requires two vectors to describe it, the blue and the purple vectors in this picture. Returning to our code, the next thing we want to do is examine the result of the line trace to see if the player is trying to use a usable object. We can first create a branch on the return value, which is a simple Boolean that tells us whether the line trace hit any object at all. We only want to do our more complicated checks if this is true. Now we can break apart the hit result to get further information about the object that was discovered by the line trace. We want to check if the actor that was hit implements our usable interface. We can use the doesObjectImplementInterface node to do this, and we can branch on the return value to check whether it does implement the interface we chose. If this is true, then we can send the object a use message. This message will only be received if it implements the usable interface. The object itself will then handle the actual response by calling its use function. You can now compile and save the main character and organize this graph before we move on. Let's return to the event graph for the main character by double-clicking on the event graph on the left. You can also jump directly to events within the graph by clicking the arrow to expand the list and double-clicking on the event. We're now going to handle the different situations that can occur when the player overlaps with objects in the world. The first thing we want to do is store the object the player overlapped with in a variable so that we can easily reference it later. Call this variable overlapped actor. We now want to create a branch based on whether the player is currently holding an object. If the player has nothing in their hand when they overlap an object, then we might want to allow them to pick up the object. But if they are already holding something, then we do not need to check whether they can pick up the object because for now, our player can only hold one object at a time. But we still need to make some other checks because if the player is holding something, they might be trying to unlock a lock using the key in their hand. We will create this branch by asking whether the player's held actor variable is valid. An object reference variable is valid only if it is storing a reference to an object, and it is invalid if it has no reference. You might want to give yourself a little more room because these two paths will need a decent amount of space in the graph. We will first handle the isValid path. If this path is being executed, it means that the player is currently holding an object. Let's start by checking if the object they overlapped with implements the unlockable interface. If this is true, then we can send an unlock message to the object. Remember that this message requires an input that it can pass on to the object's unlock function. The input is the actor object the player is trying to use on the lock. We can pass the held actor reference to this input. We know this reference has a valid object because of the path that is currently being executed. To complete this path, we first want to check if the unlock attempt was successful. If this is true, then we will set held actor to none. This is because the key is now in the lock and no longer held by the player. To set a variable to none, you simply pass the set function no input. Now let's handle the isNotValid path. If this path is being executed, it means the player does not have any object in their hand. In this case, we want to check if the object they just overlapped with implements the pickup interface. If this is true, then we can send the pickup message to the object. The pickup message will return an output that we can use to check whether the object was successfully picked up. The player can fail to pick up an object if it is a key that has already been placed in a lock. In this case, the key is held in place and can no longer be picked up. If the pickup action succeeded, then we want to take the overlapped actor and attach it to the player's hold point component that we created earlier. We can use the Attach Actor to Component node to do this. The target should be the overlapped actor reference, and the parent will be the hold point scene component. After the object is attached to the player's hold point, we want to set its relative transform. The reason we are doing this is to decrease the scale of the object so it takes up less space in the player's field of view. Later on, when the key is placed onto a lock, we will immediately change the scaling back so that it looks correct again. From the player's perspective, they won't be able to tell the scaling occurred at all. This is a common visual trick where objects are scaled in certain ways to affect how they appear for a particular camera angle. You can look up a good example of this where the animator Tony Bonilla shared some behind-the-scenes shots from Encanto that revealed the character's model with dramatically stretched arms. You can see a comparison of what the scene looks like from the camera and what it looks like from the side. On camera, the extra distance between the character's face and their hands creates a dramatic effect even though it looks completely wrong from any other perspective. The last thing we will do on this path is set the held actor variable to the overlapped actor. This is because the player has just successfully picked up this key, and now we want to keep track of the key they are holding with our held actor variable. This completes both paths for the begin overlap event. We can now begin working on the door blueprint. Let's start by going into the door folder. We are going to create all of the materials that we will need when building the door, lock, key, and switch blueprints. First, create a material called m_door. This is going to be a dynamic material that has its color changed from within the blueprint. In order to do this, we need to create a vector parameter that we can use to control the base color of the material. Call this parameter door color. You can set this parameter to a default color just to distinguish it while we are setting up the door, but the color will be completely controlled by the blueprint logic. For the rest of the materials, you can pick any style you prefer. They will not affect the code in any way. Create a material called m_pedestal. We will use this color for the stand that holds the lock for each key. The lock itself will use the door material. Create a material called m_frame. This will be the material for the outer parts of the door that do not move. You can think of it as the wall that the door is built into. Create a material called m_switch. This will be the material for the base of the switch. The switch button itself will also use the door material. Now that we have all of the materials we need, let's also create the 4 blueprints we will be building. All of these blueprints will inherit from the actor class. Create one blueprint called BP door, one called BP key, one called BP switch, and one called BP lock. Let's start with the key blueprint. The first thing we want to do is implement the pickup interface. This will give the blueprint a pickup function. This function will automatically be called whenever this key receives a pickup message. As you can see, the function already has the correct output defined for us because it got this information when it implemented the pickup interface. Let's build out the components of the key blueprint. Add a sphere collision component as a child of the default scene root and name it sphere collider. Add a scene component as a child of the sphere collider and call it key mesh. We will usually use a single scene component as the parent for all of the meshes associated with our actors to help keep them organized. Remember, you can't see a scene component in the game. It simply gives you a reference to a particular location. We will build the key mesh out of 4 cones that will be arranged in a star shape. Add 4 cones as children to the key mesh component. Name them ray left, ray right, ray top, and ray bottom. We will move them into the correct places shortly. Now, let's define the variables this blueprint will need. Define a variable called linked door and set its type to be a BP door object reference. This will allow each key to have access to the door that it can open. Next, define a Boolean variable called isPlaced, then a second Boolean called isMoving. Define a single float called speed, then define 2 floats called motion amplitude and motion height. We will talk about what these variables do in more detail when we start to use them in the code. We will now arrange the mesh and apply the materials. Select the sphere collider and change the Z value of its location to 100. This should also move the mesh if you have everything parented correctly. Increase the sphere radius for the collider to 36. You also want to make sure the sphere collider and all of its children are set to movable for their mobility, because we are going to animate the keys when they are freely placed in the level. We will now go through each of the cones and arrange them to create the star shape. Select ray left and set its location to 0, 12.5, 0. Set its rotation to 90, 90, 0. Set its scale to 0.25, 0.0625, and 0.25. Watch the screen to make sure your cone moves in the same way as a guide. You can also assign the door material to each of these rays as we go. Now select the ray right cone. Set its location to 0, minus 12.5, 0. Set its rotation to 90, 90, 0. Set its scale to 0.25, 0.0625, and negative 0.25. Assign it the door material. Select the ray top cone, set its location to 0, 0, 12.5, set its rotation to 0, 0, 90, set its scale to 0.25, 0.0625, and 0.25 again. Assign it the door material as well. Finally, select the ray bottom cone, set its location to 0, 0, minus 12.5, set its rotation to 0, 0, 90, and set its scale to 0.25, 0.0625, and negative 0.25. Make sure to also set its material to the door material. You should now see the full star shape we will be using for the key. If something is out of place, check the minus signs to see if you missed one. We are now going to write the function that will update the color of the door material for the key. This same material will be used on the door, the key, the lock, and the switch. We will set it up so that we can assign a single color to the door in the editor, and then all of the items that are connected to that door will update their color to match the door they belong to. In order to do this, each item will have its own update color function that will be called by its linked door whenever the door's color is changed. Let's create a new function called update color. We need to give this function an input called indoor color and set its type to linear color. For the key, we will actually need to update 4 different meshes because each ray uses the door material to give the whole star a single color. In Update Color, we can use a reference to the key mesh component and a node called getChildrenComponents in order to get an array of all the cones which are its children. Now that we have that array, we can use a for each loop to iterate over each of these children. In the loop body, the first thing we need to do is cast the array element to a static mesh component. This is because the array returns a generic scene component reference. This is a generic parent for components like our cones. But remember, a scene component has no visual element, so we can't do things like update its material. In order to safely change the material, we have to confirm in the code that this really is a static mesh component and not just a generic scene component. We can do this by casting the element. If this cast succeeds, then we are given a new reference to the child that is fully aware it is a static mesh component with a material. If the cast had failed, that would mean we have a child that is not a static mesh component. Instead, it would be one of the other components that has scene component as its parent. We can use the static mesh reference to create a dynamic material instance of the door material. This allows us to basically create a local copy of the door material for this particular key so that it can change the color of the material without affecting all of the other objects that use the same material. For instance, we will have multiple doors, each with their own key, and we don't want the color change to affect every door and every key. We only want it to affect the door and key that are linked together. The dynamic material instance allows us to do this. We have to select the source material that we're trying to create an instance of from the dropdown. Now that we actually have a copy of our material, we can update the door color vector parameter that we defined earlier in the material graph. When doing this, we have to be very careful to use the exact same name we defined in the material. Sometimes it helps to even go back to the material and copy the name so that you can paste it directly into this field without worrying about typing it correctly. Finally, the value we want to use for the color is the value that will be passed into this function as an input. When the door has its color changed in the editor, it will call this function on its keys and then pass the new color to the function. Now we have a working update color function for our key blueprint. The next thing we will do is define the function that will animate the key when it is freely placed in the world. Create a new function called updateMotion. This function does not need any inputs or outputs. The very first thing we will do is check to see if this key should be moving. When a key has been placed into a lock, it will stop moving and be frozen in place, so we want to make sure it no longer continues to animate at that point. We will control this by updating the isMoving variable to false. If isMoving is true, then we are going to apply two different movements to the key. We are going to rotate the key around its z-axis, and we are going to make it float up and down. To do this, we will first get the current game time in seconds. We will use this as an input to drive our animation. We will take this time value and multiply it by 2 pi and the speed variable we defined earlier. We can then use this as the input angle for a sine function. This will give us an output that gradually moves back and forth between -1 and 1. We can then scale that output by our motion amplitude. This variable will define how high the key floats upwards relative to its starting position. Finally, we will add the motion height to the output so that the key floats a certain height above the ground. Without this last addition, the key would float in and out of the ground at z = 0. Now it will float around z = motion height. We now want to make a new vector to define where to place the key as it moves. We can use the value we have just calculated as the z value for this vector. Now you can make some room for the second calculation. This is where we are going to calculate the rotation of the key that will happen alongside the floating motion. We will use the same input angle to drive this rotation so that the key rotates and floats in a way that is nicely aligned. Take a second wire from the angle value and begin by converting it to degrees from radians. Then divide that angle by 2 by multiplying it by 0.5. We can now use this as the z value for a new rotator. The key will rotate half as fast as it floats up and down. This will ensure they stay nicely lined up, one rotation for every 2 floats. All we have to do now is use the vector and rotator to create a new transform for the key object. Use a set relative transform node to apply these motions to the sphere collider. This collider is the parent of all the meshes, so they will all rotate in the same way along with it. You can take a few moments to clean up this function because it is now complete. Also remember to compile and save the blueprint to avoid losing any of this work for the last 2 functions. The next thing we are going to do is write the pickup function that is called whenever a key receives a pickup message. The first thing we need to do is check whether this key has already been placed into a lock. In that case, it will be held in place and not able to be picked up again. We will create a branch on the isPlaced variable to check this. If this value is true, then the only thing we need to do is return false for the outSuccess variable. This will inform the caller of the function the key was not picked up. But if isPlaced is false, then the key is available to be picked up. In this case, we want to reset its relative transform. This is because the key was previously being animated and it will likely be translated and rotated to a different position. We can then set isMoving to false to ensure the key no longer animates while being held by the player. And finally, we can return true for outSuccess to complete this path because the key was successfully picked up by the player at this point. This completes the pickup function. We can finish up with the key for now by going to the tick event and calling the updateMotion function every tick. This will make sure each key is animated when its isMoving variable is set to true. We can now move on to working on the lock blueprint. Remember, you can bring up the Open Asset window by pressing Control-P on Windows or Command-P on Mac. This allows you to quickly jump to different assets in your project. We will begin with this blueprint in a similar way. Open up the class settings and implement the unlockable interface. This will provide the blueprint with an unlock function, which it will use to respond to unlock messages. Let's set up all the components we will need for the lock. Add a box collision component as a child to the default scene root and name it Box Collider. Add one scene component called Key Location. Now add two scene components and call them Pedestal Mesh and Support Mesh. Then add two cube components as children to the pedestal mesh. Call these Platform and Base. Make sure they are siblings, meaning they are both children of the pedestal mesh. Add two cube meshes as children to the pedestal mesh. Call them Platform and Base. Make sure they are siblings. Now add two cones as children of the support mesh. Call them Cross 1 and Cross 2. This will be the part of the mesh that actually holds the key. It will also have the door material that can be changed in the blueprints. Just like we did with the key, let's also add a variable called linked door that will be a BP door object reference. Now we can place all of the components in their correct positions to design the lock. First, select the box collider and change the Z value of its location to 50. Change the box extent for the collider to 100, 100, 50. This will determine the area around the lock where we will check whether the player has the correct key to place onto the lock. So we want it to extend far enough out so the player can walk into this area. Select the pedestal mesh component and set the Z value of its location to -50. Now select the platform mesh and set its location to 0, 0, 85. Set its rotation to 0, 0, 90. Set its scale to 0.5, 0.5, 0.1, then assign the pedestal material. Then select the base mesh and set its location to 0, 0, 40. Set its rotation to 0, 0, 90. Set its scale to 0.2, 0.2, 0.8, and assign the same pedestal material. Now select the support mesh component. Set the Z value of its location to -50. Select the cross 1 mesh and set its location to 0, 0, 105. Leave its rotation at 0, 0, 0. Set its scale to 0.05, 0.3, 0.3. Then assign it the door material. Then select the cross 2 mesh and set its location to 0, 0, 105. Set its rotation to 0, 0, 90. Set its scale to 0.05, 0.3, 0.3, and assign it the same door material. The last thing we need to do is place the key location component that we will use as a target when we place a key on this lock. Set the value of its location to 50. Take a look around the lock and make sure everything looks like it is placed correctly. We will now write the unlock function that is called in response to any unlock messages. Open the function by double-clicking on it from the functions list on the left. The first thing we need to do is check whether the object the player is attempting to use is actually a key. We can do this by attempting to cast it to the BP key class. If this cast fails, then we can immediately return false for out success. But if this cast succeeds, then we need to perform another check to see if this is actually the correct key for this particular lock. In order to do this, we need to extend our door blueprint. We are going to add a variable to the door called linked key. Set its type to BP key and make sure it is public so that it can be referenced by another class. Compile and save the door blueprint and then return to the lock blueprint. Now we can use a reference to the linked door to get its linked key. We then want to compare the key that was linked to the door with the key that the player is currently trying to use to open this door. If this branch returns false, then this object is a key, but it is the wrong one for this door. That means we can return false for out success. The unlock attempt has once again failed. But if this is true, then we are going to need to handle the process of placing the key into the lock. We can begin doing this by once again getting a reference to the linked key from the linked door. Pull the wire out for the linked key and then search for the Attach Actor to Component node. It should connect the linked key to the target input automatically. Then we can use the key location component as the parent. This will attach the key actor the player is currently holding to the key location component on this lock. It will automatically detach the key from the player's hold point that we originally attached it to. We now want to position the key correctly relative to its new position on the lock. Make a new transform and set the Z value of the location to 25. Notice this will also reset the scale to 1, 1, 1. Remember, we shrunk the key when the player picked it up. Use this transform as the new relative transform for the linked key by adding a Set Actor Relative Transform node into the graph. The next thing we want to do is update the isPlaced variable for the linked key to true. To complete this path, we once again need to extend our door blueprint. Return to the door blueprint and add a new variable. Call it linked switch array. Set its type to BP switch, and then set this variable to be an array by using the small drop-down right next to the type in the details window. The reason we need to use an array here is because each door can potentially have multiple switches that open the door. In our design, we are going to have a switch on both sides of the door so that it can be opened from either side. But you could also add more than 2 switches and the design would work exactly the same. Make sure this variable is also set to public and then compile and save the door blueprint. We can now return to the lock blueprint and finish the path we were working on. Get a reference to this new linked switch array using the linked door reference. Then use a for each loop so that we can iterate through this array. We now need to do a little work on our switch blueprint so that it has the functionality we need to finish the lock. Open the switch blueprint and add a new variable called isActive. Set its type to Boolean and also make it public. Compile and save the switch blueprint so this variable is available. Return again to the lock blueprint so that we can finally complete this path. When a door is unlocked, we are going to go through all of its switches and set them to be active. This will make it so each switch can now open and close the door. Before the door is unlocked, its switches will all be inactive by default so that they do not work until the lock is released. Finally, when this for each loop is completed after looking at each switch object, we are also going to open the door by sending it a switch message. The door blueprint will implement the switchable interface, meaning that it can be switched to be open or closed. Normally, these switch messages will always be sent by the switch objects that are attached to the door. but we are also designing it so the player doesn't need to go over and press the switch the first time they unlock the door. You can feel free to change this in your own code if you would prefer that the player always had to use the switch to open the door. You would simply need to remove this switch message, but make sure you keep the part that activates all of the switches so they can now be used to open the door manually. At the end of this path, we can return true for out success after the switch message. This is the one path where the lock has been successfully unlocked by the player. You can now take a moment to clean up this graph and review it quickly to make sure everything is in order. One thing that is easy to miss is making sure the checkboxes are set correctly on all of the return nodes. We can now write the update color function that sets the color of the lock to match the color that was set on the door. This is going to be very similar to the update color function we wrote for the key blueprint. Add a new function called updateColor to the functions list, and then give it an input called inDoorColor with the type linear color. We're going to follow the same pattern we used for the key. Get a reference to the support mesh, and then call getChildrenComponents on it. We can now use a for each loop to iterate over the two support meshes. Cast each element to a static mesh component, then use that new static mesh reference to create a dynamic material instance. Select the door material as the source and then call setVectorParameterValue on the new dynamic material instance. Once again, be careful here because the parameter name needs to be exactly the same as the one defined in our door material graph. If you're unsure, you can go back to the material and copy the name. Finally, pull the input wire across so that it can be used as the value for the door color parameter. This will update the color of both support meshes to match the color passed in as an input. That completes the update color function, and it also finishes up most of the work we need to do on the lock. Let's now move over to working on the switch blueprint. We'll start by going into class settings and implementing the usable interface for this class. This will give us a use function that will automatically be called whenever a use message is received. It's worth taking a moment to explain the distinction between the switchable and usable interfaces. In the design we are using for this project, the door will have the switchable interface, and each switch will have the usable interface. The idea is that a switchable object is an object that can be in one of two states. The door can either be open or closed. And a usable object is any object that can be interacted with through a use input action. Originally, the switches were going to have two states, pressed or released. But in the final project, they are acting more like buttons that are pressed and returned to the unpressed state automatically. This makes switch a rather confusing name for these objects. We'll come back later and rename them to button to avoid this confusion, but for now just know that the door is a switchable object and the switch is a usable object. Let's now define the components for the switch. Start by adding a box collision component and call it box collider. Now add two cube components as children to the box collider. Call them base and button. We'll come back and place them correctly in a moment. Add a new variable called linked door and set its type to a BP door object reference. Compile and save the switch blueprint. Now we will define the update color function that we have defined for all of the other blueprints. Add update color to the functions list and give it an input called indoor color with the type linear color. This version of the function will be simpler because we do not need to iterate over components. The button is the only component that needs to have its color updated. Follow the same pattern. Create a dynamic material instance on the button, then set its source to be the door material. Then call setVectorParameterValue and pass it the door color parameter name and the indoor color input value. We will now define the response to the Use input action. Double-click on Use under the Interfaces section on the left. You might notice that for the usable interface, we are actually given an event called Use instead of a function. If you define an interface function that has no inputs or outputs, then it will be implemented as an event. This is because events are a little more versatile than functions, so when possible you are provided with an event to give you a bit more flexibility in your code. For instance, you cannot use a delay node in a function because a function must complete its entire execution after it is called, whereas an event can issue a delay, then complete its work after the delay has finished many ticks later. We are going to animate the button when it is pressed. In order to do this, we will introduce a new timeline. Right-click on the event graph and search for Add Timeline. This will introduce a new timeline node into the graph. Name it Switch Action Alpha. Double-click on the title bar of the timeline node to open up the timeline editor. Add a new float track to the editor and call it Alpha. We want to add two keyframes to this track. If you hold Shift and click on the graph, you can insert a new keyframe. You can then click on each keyframe to precisely position it. Set the first keyframe to time 0 and value 0. Then set the second keyframe to time 5 and value 1. You can now select both keyframes by holding Shift, and then if you press the number 1 on the keyboard, it will automatically smooth the transitions between them. We're going to use this timeline to smoothly drive the animation of the buttons when the player uses them. Let's now return to the event graph and finish up the Use event response. Whenever the player attempts to use a button, we first want to check whether the button is already moving. This means it was just pressed and its animation hasn't finished yet. In that case, we don't want the player to be able to use the button again until it has finished. To do this, we can get a reference to the timeline we just created and then call isPlaying and create a branch with the return value. We only want the use response to continue if the timeline is not currently playing. So on the false path, we can get another reference to the switch action alpha timeline and call play from start to begin execution of the timeline we defined with the keyframes. The next thing we want to do is check if the button is active. This is because we always want the player to be able to press the button even if it does not currently open the door. Because even though the button can't be used to open or close the door, the player can still simply press the button. So we need to check if it is active only after starting the animation. But if the button is also active when the animation starts, then we can send a switch message to the linked door. This will trigger the switch function on the door, which we will write shortly. This function will switch the door between open and closed. Now let's take a moment to position the switch's components correctly. Return to the viewport for the switch and select the box collider. Set its box extent to 25, 25, 10. Now, select the base mesh. Set the Z value of its location to -5. Then set its scale to 0.5, 0.5, 0.1. Finally, assign it the M_switch material. Now select the button mesh. Set the Z value of its location to +5. Then set its scale to 0.35, 0.35, 0.1. Finally, set its material to the door material. Also, make sure that its mobility is set to movable because this is the part that will be animated. Compile and save the switch blueprint. Take a look at the meshes in the viewport and make sure everything looks like it is placed correctly. Also, make sure to check the box collider shape. It should perfectly surround the meshes we just defined. We now want to apply the animation to the switch using our timeline. Return to the Use event by double-clicking on it from the event graph on the left. Make some space to the right of the timeline node so that we can define the animation. What we want to do is use the alpha value that is produced every timeline update in order to change the Z value of the button's location. We can do this by defining a linear interpolation between the two Z values where we want the button to be during its animation. Think of a linear interpolation like a slider. The slider can be set to any position along its track. We will call this position alpha, and we will define alpha to go from 0 up to 1. You can also think about this as the percentage of the distance from the left to the right of the slider. For instance, if the slider is halfway, the alpha would be 0.5 or 50% of the way across the track. Now, imagine that the slider is controlling a point that moves through space. The point will start at a position called A when the slider is at alpha equals 0 on the far left, and the point will move to a position called B when the slider is at alpha equals 1 on the far right. So another way of thinking about the linear interpolation is that it converts the number alpha into a related position on this line between points A and B. This is where the word linear comes from. Interpolation essentially means changing smoothly between two different states. So a linear interpolation moves a point between two positions by following a line to get from A to B. And alpha tells us how far along the line we currently are. If the slider is placed at alpha equals 0.5, then the point will be 50% of the way along the line between A and B. Add a linear interpolation node into the graph. You'll notice it is also called a lerp for short. Set its A value to 5 and its B value to -3. When you're designing animations yourself, you can find these values by just going to the viewport and moving the components around to where you want them, and then reading off the location values from the details window. Also, notice that the linear interpolation does not need to increase from A to B. If A is greater than B, like it is in our case, that simply means the line that connects them will have a negative slope instead of a positive slope. Since we are going to be setting the relative location of the component, we don't need to worry about the X or Y at all. We just want those to stay exactly where they are, so the button only moves up and down, not side to side. Finally, call setRelativeLocation on the button component and pass in the vector for the new location input. Our timeline updates are now finished. These updates will be triggered by the Play from Start node we called up above in the Use event response. We now have all of the supporting blueprints pretty much finished, which means we can begin work on the door itself. Open the door blueprint and begin by going to Class Settings and implementing the switchable interface. This will give us a switch event that will automatically be called whenever the door receives a switch message. Notice again, this is an event and not a function because when we defined switch, we did not give it any inputs or outputs. Let's set up the components for the door. Begin by adding a scene component to the default root and call it door mesh. This will be the parent for all of the moving parts of the door. We will form the door from 4 panels that will all move in their own direction. Add 4 cube meshes as children to the door mesh component. Call them panel lower left, panel lower right, panel upper left, and panel upper right. These names will help us keep track of where they should be while we design the door. Now, add a second child to the default root component and call it frame mesh. This will be the parent for all of the surrounding parts of the door that do not move when it is opened or closed. Add 3 cube meshes as children to the frame mesh component. Call them frame top, frame left, and frame right. We will not need a frame below the door because that is where the floor will be, but you can easily change this design if you want doors that are suspended up above the floor somehow. We also want to add a variable called linked lock that has its type set to a BP_lock object reference. Make sure this variable is public. Add another variable called door color that has the type linear color. This is going to be the main source for the color that will be applied to all of the other blueprints. When we update this color on the door, it will be passed down to all of those other update color functions we defined so that all of the blueprints associated with a particular door will have matching colors. Also make sure this variable is public. Add a Boolean variable called isOpen that simply defines whether the door is currently open or closed. Finally, define a float variable called door alpha. This will be a timeline alpha value that we use for animating the 4 panels of the door. We are going to store it in a variable for convenience so that we don't have to use so many wires in the graph to access its value as we animate the door. We are now going to define the update color function for the door, but this is going to be significantly different from the functions we defined for the other blueprints. The reason is that the door is in charge of updating its own color, but it also coordinates the color change of all of its connected blueprints. Create a new function called updateColor in the functions list. You can also select Call in Editor in the Details window for this function. This means we will be given a button that allows us to call this function manually from the editor as opposed to only being able to call it from blueprints. This function actually doesn't need a linear color input because it is simply going to read the linear color that is set in the door color variable we just defined. The first part of this function will look very similar to the other update color functions we wrote. Start by getting all of the children of the door mesh component and iterate through them using a for each loop. Cast each array element to a static mesh component, then create a dynamic material instance for the component. Select the door material as the source. Finally, call setVectorParameterValue on the material instance and pass it the door color parameter name, and then use the door color variable we defined as its value. Since this function is going to have a lot of nodes, we are going to organize it a little better using a sequence node instead of writing everything out as one long line. Go back to the beginning of the function and introduce a sequence node right after the entry node into the function. A sequence node simply calls all of its output wires in order, starting with then 0 and going down the list. It doesn't change anything about how the nodes are executed. We could write this same function without it by just continuing the line of nodes, but it's nice to use a sequence node when the work you're doing can be split into pieces conceptually. On this path, we're going to check if this door has a valid reference to a key in its linked key variable. If it does have a valid key attached, then we want to call the updateColor function for that key and pass in the door color variable as its input. We'll do almost the exact same thing for the linked lock variable. First, add a then_to pin to the sequence, then check if there's a valid lock reference, and call updateColor on that lock, passing it the correct input. Finally, add a then3 pin to the sequence. In this case, we have to deal with the fact we might have multiple switches stored in an array. So we just have to iterate over the linked switch array and then call updateColor for each switch we find. We don't need to check if each switch is valid because switches are only added to the array when they are actual switch objects. If there are no valid linked switches, then the array will just be empty and nothing will happen when the for each loop runs. That's the entire updateColor function for the door. You can take a moment to organize the sequence and all of its paths. Let's now work on the animation timeline for the door. Introduce the switch event into the graph by double-clicking on the interface entry for switch. We can add a new timeline node into this graph and call it Door Action Alpha. Double-click on the timeline to open its editor. For the door animation, we will add 3 keyframes. For the first keyframe, set its time to 0 and its value to 0. For the last keyframe, set its time to 5 and its value to 1. Place the middle one wherever looks correct to you. To complete the setup, select all 3 keyframes and press 1 to smoothly connect the points. Let's now set up the animation of the door based on the alpha value that is produced by the timeline node. Our first step is to store the alpha value in the door alpha variable we created earlier. This is only for convenience. The animating code is going to be slightly complicated, and it is going to use the alpha value multiple times. We are storing it in a variable to limit the number of wires in the graph. We will now add 4 lerp nodes, one for each panel of the door that will be animated. We will then create 4 new vectors that will define the next position for each panel based on the output of its related lerp. For each panel, there will be one coordinate that is being changed. For the first lerp, connect the return value to the y value. For the second, connect it to the z value. For the third, connect it to the z value again. And for the fourth, connect it to the y value. The final step for each path is to update the relative location of the relevant panel. We will also introduce a sequence node to help organize the handling of the 4 panels. Connect the output of each vector into the new location for its related panel. Now, plug in the door alpha variable for each of the lerp nodes. They are all being driven by the same curve. The difference is simply where they begin and where they end when producing the one varying coordinate for the vector. To complete the animation, we need to set the correct starting point and ending point for each panel's lerp. To help understand where these numbers are coming from, remember that you can go to the viewport and simply move each panel while paying attention to the location in the editor. You will be able to directly see what the A and B inputs should be for each panel. We'll now go through each panel. For the upper left panel, set A to 100 and B to 299. Then set the Z value of the output of the vector to 300. The reason we are using 299 is so that the panel stops right before it completely disappears into the wall. This prevents a visual glitch known as Z-fighting, where two faces are at the exact same position, causing them to flicker. If you do want the panels to completely disappear into the wall, you could also fix this problem by going 1 unit farther instead of stopping 1 unit short. In this case, you would set B to 301. Now move on to the lower left panel. Set A to 100 and B to -99. Then set the Y value of the vector to 100. Now move on to the upper right panel. Set A to 300 and B to 499. Then set the Y value of the vector to -100. Now move on to the lower right panel. Set A to -100 and B to -299, then set the Z value to 100. If you also copied these nodes to create each path like I did, then double check to make sure you have the right nodes for each panel. For instance, I had to fix the last one to use the lower right panel. This completes the animation of the door in response to the timeline. Let's now define the door's reaction to the switch event. Double-click on the switch entry under the interfaces list. This will introduce the event into the event graph. You can also clean up the graph by deleting the default events that we don't need right now. This will be very similar to the way we handled the pressing of the button using the timeline. Start the response by checking the isPlaying value for the door action alpha timeline. We only want to run the animation again if it is currently not playing. Next, we will check to see if the door is open using the isOpen variable we defined. Branch on this value and create two paths where we can handle both cases. If the door is currently open, then the true path will be executed. In this case, we will set isOpen to false because we are now closing the door, and then we will call reverse from end on the door action alpha timeline. This runs the timeline we've created in the opposite direction from how we defined it. So the alpha value will start at 1 and then smoothly go back down to 0. For the other path, where the door is not currently open, we will set isOpen to true because we're now opening the door. And then we will call play from start on the door action alpha timeline. This completes the response to the switch event for the door. Double check the two paths because it can be easy to mix up the set for the isOpen variable. It is always being set to the opposite of its current value. If it is open, we are closing it, and if it is closed, we are opening it. Now open up the construction script, which is run every time the door is created in the world. On construction, call the update color function we defined earlier. This will make it so that the full color update is run when we place a door into the world or when the door is recreated by the engine. Now, let's place all of the components correctly to design the appearance of the door. Select the lower left panel, set its location to 0, 100, 100, set its rotation to 0, 0, 90, set its scale to 2.25, 2. Also, make sure that the mobility is set to movable because these are the animated parts of the door. Finally, assign the door material to the panel. Now, select the lower right panel. Set its location to 0, -100, 100. Set its rotation to 0, 0, 90. Set its scale to 2.25, 2, and set its mobility to movable and assign the door material. Now select the upper left panel. Set its location to 0, 100, 300. Set its rotation to 0, 0, 90. Set its scale to 2.25, 2, and set its mobility to movable and assign the door material. Now select the upper right panel. Set its location to 0, -100, 300. Set its rotation to 0, 0, 90. Set its scale to 2.25, 2. Set its mobility to movable and assign the door material. We can now place the frame meshes. Select the frame left mesh. Set its location to 0, 300, 200. Set its rotation to 0, 0, 90, and set its scale to 2.5, 4. These may be movable by default, but they do not need to be because the frame will not be animated. But make sure to assign the frame material to these components. Now select the frame top mesh, set its location to 0, 0, 500, set its rotation to 0, 0, 90, set its scale to 8.5, 2, and assign the frame material to the component. Finally, select the frame right mesh, set its location to 0, -300, 200, set its rotation to 0, 0, 90, set its scale to 2.5, 4, and assign the frame material to the component. That completes the design for the door. Compile and save the blueprint. We now finally have all of the blueprints mostly complete, and we can move on to setting up the level to test out the features we've created. Open up the level in the editor. Use the Add Object button at the top of the editor to add a BP_door actor into the scene. You can then duplicate this actor 2 more times so that you have 3 doors in total. You can duplicate using Ctrl-D, or you can right-click on the door in the outliner and choose Duplicate. Now, add a BP lock actor into the scene and duplicate it twice as well. Then do the same for the BP key. Finally, we want to add a BP switch into the level and duplicate it 5 times. We are going to have 2 switches for each door, so we need 6 in total. Rename the switches so that they end with 1A, 1B, 2A, 2B, 3A, and 3B. This way they will match up nicely with the numbers for the connected door. You can place the actors in the level in any way you prefer. They will be connected through the blueprints. Their position in the level doesn't affect how they work at all. We now want to link together all of our actors. You will find the variables in the Details window after selecting one of the actors. You want to make sure the numbers match up, so door 1 should be linked to key 1 and lock 1. And then you can add 2 switch references to the linked switch array and make sure they also have the matching numbers, so that door 1 is linked to switch 1A and switch 1B. We now have to go through all of our actors and make sure their links are set up correctly. After finishing with the doors, make sure you move on and do the keys, locks, and switches as well. If you don't see one of the variables in the Details window, then it might not be set to public. In this case, you can simply return to the blueprint, click on the closed eye icon next to the variable to make it public, then compile and save the blueprint. Return to the level editor and you should now see the variable under the Details window. You can also finish up placing the actors throughout your level. The switches do not need to be placed on the doors, they can also be placed anywhere in the level. You can see that for the lock, I did forget to make the linked door variable public. So open the door blueprint and make this variable public so that it can be accessed in the level. We have the same problem with the switch. Also make its linked door variable public. Now that everything is in place and linked together, we can test out the update color functions. If you go to one of the doors and bring up the color picker for its door color variable, you should be able to change the color of the door material. If everything is set up correctly, then you should also see the color of its key, lock, and switches changing in the same way. You can also use this to see if they are linked correctly. Go through each of your doors and assign them whatever color you prefer. Let's now test out the functionality of the doors by playing the level. The first thing we want to check is whether the switches can be pressed before interacting with the key or lock. Remember, the player should be able to press the switch at this point and see it move, but there should be no response from the door. So it looks like we're not yet seeing the button press response. Let's take a look at the blueprints to figure out what is missing. We will use a print string after the use event is triggered to see if the event is happening at all. Once we play the level again, we can see that the use event is not being executed. Let's now check to see if the use input action is being triggered, because this input action is what eventually executes the use event. Open up the main character blueprint and place another print string after the entry into the use action function. Okay, so now we can see where the problem must be, because we do get a response from the use input action, but we do not ever execute the use event. This means the problem must be in between when we are running our line trace to see if there is any object close enough to the player for them to use. We can look at the line trace in the main character class. Let's see if we set up the default values for the variables. It looks like the use distance variable is still set to 0 by default. This is causing our problem. The use input action successfully triggers this line trace, but then the line being used has a length of 0. Our line starts at the camera's world location, and then we essentially add the 0 vector to that location, so the end is also at the same location. This happens because the used distance is 0 and we're multiplying it by the vector we were trying to add. Let's fix this by setting a non-zero value for the used distance. We will set it to 250 centimeters. Okay, play the level again and test out whether you see the line trace and can now press the buttons. It looks like we have solved our first bug, but discovered a second bug. The button is now being pressed, but we can see two issues. The animation is far too slow, and the button only goes down. It does not return back up again. We can fix both of these problems by going back to the timeline we are using to animate the switch. Open the switch blueprint, go to the event graph, and double-click on the switch action alpha timeline to open the editor. We want to shorten the length of this timeline so that the animation is much faster. Change the length from 5 to 2 seconds. We also want to introduce a third keyframe so the button can go down during the first part of the animation and then return back up again during the second part. Set the second keyframe to time 1 and value 1. Then set the third keyframe to time 2 and value 0. Now we can select all 3 keyframes and press 1 on the keyboard again to smoothly connect them. Compile and save the blueprint, and let's test out the switch animation again. This looks much better. The switches appear to have the correct animation behavior, and they are not affecting the doors before they are unlocked. Now, let's test out the keys and locks. You should be able to pick up one of the keys by walking close to it. You should see the key being held in the lower right section of the screen. Remember, we also scaled the key down so that it would take up less of the player's view. If you walk around, the key should stay with you. But you probably notice another bug in our design. It appears that when holding the key, the player's movement is a bit hindered. It's almost like the key is pushing the player. Open up the key blueprint so we can take a look at it. If we look at the static meshes we used to create the rays, we can see they actually have some collision on them by default. We do not want this to be active. It is causing the player to collide with the key while they are holding it. Let's go through each of the ray meshes and set its collision preset to be no collision. But after you've done this, make sure the sphere collider still has its overlap all dynamic preset, because this is what allows the player to pick up the key when they overlap with it. Let's now test out the level again. You should be able to pick up one of the keys and freely move around without being pushed. Now that this is fixed, let's see if we can interact with the locks. First, walk up to one of the incorrect locks. Nothing should happen. You should continue to hold onto the key because it checks to see if this is the correct lock and does nothing if it is incorrect. Walk up to the correct lock. When you get close, the key should suddenly snap into place on the lock, and then the door's opening animation should begin automatically. It looks like this is almost working perfectly. You can now see how each panel stops moving just a little bit before it fully enters into the wall. Let's now check to see if we can close the door using the switch, because the switches for this particular door should now all be active. Okay, it looks like the switches can also be used to close the door. Let's go test whether we can now pick up another key and open its linked door. It looks like the other doors are also working. You can also attempt to use the button multiple times when the door is moving. What should happen is the button can still be pressed, but nothing will happen until the door has finished its animation. Only then will the switch be able to open or close the door again. This all looks like it is now working correctly. You can also test to make sure both switches work for each door. The one thing that still isn't quite right is the placement of the key when it is on the lock. It is a little bit low. Let's open the lock blueprint and fix that. We simply have to move the key location scene component up until it matches with the top of the cross support meshes. After you've made this change, compile and save the lock blueprint and return to the level. Okay, now it looks like the key sits perfectly right at the top of the support. We've now tested all of the major features of the door system. The last thing we want to do before finishing up this project completely is make the name change I mentioned earlier. Our switch actor should actually be named something like button, because it does not behave like a light switch where it can either be on or off. Instead, it is a button that can only be pressed. Let's look in the content drawer for our BP switch blueprint. We can right-click on the blueprint and choose to rename it. Give it the name BP_button. This change will then be applied everywhere the blueprint is used in our project. There is also one more place where the switch name was used that is not going to be automatically fixed by the rename we just did. We have the linked switch array variable in the door. Open the door blueprint and locate that variable in the list. You can right-click on the variable here and choose to rename it. We can now call it linked button array. Notice the type was already updated to BP button because of our first rename. To be complete, we should also update the name of the material we were using for the switch. We can now call it m_button. Now that we have completed that name change, we have completely finished all of the functionality for this project.